Welcome back to the online workshop on black holes, BPS, BMS and Integrability. This morning we'll have two talks. The first one by Miguel Tierz, the second one by Ricardo Schiappa. As usual, feel free to ask questions during the talk. To do so, you will have to unmute yourself. So the first speaker is Miguel Tierz from University of Lisbon, Faculdade de Ciências, and Miguel will talk about phase transitions, random matrices, and TT bar deformation. So please go ahead, Miguel.
Okay. Thank you very much. Thanks for the opportunity of talking in this workshop. Well, it's a great pleasure, even though it has to be done in this way, right? So thanks a lot to Gabriel and Suresh. And in general, I want to thank especially Gabriel because, as you can see, I work here in Lisbon, but not on the same campus. I'm also not from here or not from Lisbon. And he's always been extremely helpful with scientific activities. He has made things way more interesting for me in my stay in Lisbon. So thanks very much to Gabriel. Okay, so yeah, we'll be talking about these three things. It will be a bit of a panoramic talk, trying to just not to talk about a single specific result, but just give you an overview of the use of random matrix theory to study phase transitions that in principle can be relevant to gauge theories, certain gauge theories like to the Yang-Mills theory and this TT bar deformation of to the Yang-Mills theory. This is so it won't be a specific result, but an overview. Like I say, I hope I managed to connect this kind of three topics in a smooth way. This is based on joint work with Leo, who is here. He's in Lisbon, with Jorge Russo, and then with Richard Sal. Okay, this is where Richard is also here, I see. And well, Leo is doing the PhD in Lisboa. But to my surprise, more than instead of getting a PhD student, I was getting a collaborator. So I told him that he can also intervene because this is a very impersonal anyway. So if he wants to say something about the work, feel free to intervene, or at the end if you want. Okay, I think I already managed to embarrass a couple of people in just a single slide. So let me just start for real. Let me begin by telling you how I plan to organize the talk. Okay, the order doesn't follow the order of the title, right? Because what makes more sense is to talk first about random matrices. So I will give a brief introduction to random matrix theory. This involves talking about the basic definitions and what is one of the most important objects in random matrix when you study random matrix ensembles, which is the two-point kernel or reproducing kernel. And so these are basic aspects of random matrix theory that perhaps I always talk about that. So I think I've been talking about these kind of things in every single talk I've given since high school, maybe. But nowadays, this is way more popular. I think much better known because random matrix theory appears in, well, it has developed, especially in the last 2 decades, a lot. But still, I think it's good to introduce the basics. And I will also, this is not completely essential for the rest of the talk, but I would like to show how random matrix ensembles are really very much related with structured matrices. What do I mean by structured matrices? I mean matrices such a Teplitz matrix, which is a matrix whose elements are constant along diagonals. So this has this X structure. So either Teplitz or Hankel matrices are extremely related to random matrix theory. In particular, the relationship is very simple to state. Due to a very powerful Hall identity called Andreev identity, the partition functions that I compute of random matrix models are determinants of Teplitz or Hankel matrices, depending on the type of the model I consider. This is one of the ways random matrix theory appears so much in physical applications. In this case, in statistical mechanics, because as you possibly know, models, solvable models such like the 2D sync model, 2D sync models, spin chain models, etc., have determinantal representations for the partition functions, etc. And very often, for example, if you have translation invariance, you have a template symmetry in your matrix. So very often these matrices are template type, and therefore this determinant that, for example, appears in the transfer matrix formalism in statistical mechanics is a random matrix ensemble and is the partition function. So this connection is one of the reasons why random matrices appear so much in at least a subset of physical theories, mostly in statistical mechanics. Then I will mention the fact that if you, instead of considering the matrices, you consider minors of the matrices, that's to say, you have the matrix and you begin to strike columns and rows like crazy, then you compute the determinant, you have a minor of this matrix. Okay, we know that all of us know this from linear algebra, undergraduate course. And then you still have a random matrix representation for these minors. And this is the random matrix ensemble that you had for the matrix, but with insertion of a character, which is a sure polynomial typically. This is relevant because this type of sure insertions appear in many different ways. And they appear, for example, in gauge theory description. So when you have a matrix model description in gauge theory, for example, thanks to localization arguments for the partition function, you normally have the standard matrix model. But then when you study Wilson loops, you have some generalization of the matrix model description. And this is precisely with the sure insertion. So in this matrix point of view, this structure matrix point of view, now we are dealing with minors of template matrix, for example, or template or Hankel or template plus Hankel. Okay, and this is the content of a thesis I supervised in Lisbon. David Garcia was here in Lisbon a while ago. Okay, so then I will try to be talking a little bit. This is more for mathematical formalist random matrix theory, which is very powerful. And for those of you who know me or my work a little bit, you know I like this very much because it's for exact computations with orthogonal polynomials, finite n results. It's also useful for large n. But possibly the main tool in gauge theory applications, at least of matrix models, is the study of double scaling limits of the matrix model, which may lead to phase transitions. This goes back to the first applications of random matrix theory in gauge theory, where a famous paper by in the 78, I think, by Brezan, Saint-Justin, Zuber, and Parisi, a very famous CMP paper. And they kind of all the Toft ideas of large n, they were studied with a toy model, which was a field theory in 0 dimensions with matrix degrees of freedom. So that was random matrix theory application into gauge theory context. And what happens is that you have typically a parameter in your coupling constant in your theory, and then you have also the rank of the gauge group. For example, if we study UN gauge theory, you can study then, of course, as we know, the large n limit, and then take the Toft parameter constant. So you multiply n by the coupling constant, and this is your lambda, your Toft parameter, and then you can study. So random matrix theory with the saddle point method tells you a very nice way of how to carry this out explicitly. And one thing that you can find is that the partition function cannot be described with a single function for the whole range of values of the Toft parameter. So because it develops, so we are saying that it develops a phase transition. And the canonical example of this, and this goes back to 79 and 80, is the model of Gross, Witten, and Wadia, which is a unitary matrix model that appears into the Yang-Mills theory and has a phase transition. This phase transition is of third order, which is unusual in the whole of physics. If you talk with condensed matter physicists, they will be surprised. If you talk with people in random matrix theory, it's the usual thing. And we'll try to elaborate a little bit on this point. Why third order is ubiquitous in random matrix theory, but it's rare elsewhere. So we will be talking about that. And then I will be discussing other models that also appear into the Yang-Mills theory, but not only into the Yang-Mills, also in statistical mechanics problems like Dimer problem or six-vertex model problems, which led to other types of models, because the Gross-Witten is a unitary matrix model. Samir was talking about this type of models. These are models that you integrate over the unitary group. And so are the same type of, roughly speaking, about as the models that were discussed a bit on Monday. but you can have matrix models on the real line, like the Gaussian unitary ensemble, for those of you who know about that, and they can be discretized. So I will be comparing, because third order phase transition appear in both ways, the Gross-Witten-Weyl transition and the Douglas-Kazakov transition, but the underlying mechanism in the matrix model is very different, because the eigenvalues live on a space which is topologically completely different. One is compact, and the support is continuous, and the other is not compact but discretized. Okay, so this makes a whole lot of plays a big difference. And then some of these models are like I'm saying, they appear in the heat kernel in Yang-Mills theory when you have defined with the heat kernel lattice action. So I will be focusing always on the sphere because it's the simplest. Well, it's one of the simplest cases to analyze, and then I will be discussing something way more recent because this kind of things in the second. This is from 79, 80, right? And this from, well, it was studied from the 80s up to now because there's still always some things to study. No, Douglas-Kazakov is from 93. So everything I'm talking about that is really old-fashioned, but hopefully I will be able to make some connections. And then this is more new because some people have studied, this TT deformation in conformal field theory, which is now a huge subject. I will focus in extremely very specific thing, which is a very nice paper by Riccardo Conti and Roberto Tateo, Stefano Negro and Leonardo Janella, that they studied the TT deformation for a number of systems, of gauge theory systems, and then at the end of their paper, they focus on, they just commented on the first steps of studying precisely these theories that I was mentioning here, these 2D gauge theories on the sphere, and then they will TT deform. So what we did with Leo was to see how this TT deformation affects the Douglas-Kazakov phase transition. And then the idea was to comment on the Q-deform version. This is the last paper we have from last week with Richard and Leo. But I think, as you can see, I'm a very redundant person. And I think there will be possibly no time. But maybe I can comment without the slides, or some of my colleagues here can just intervene because I feel like I'm talking to a screen. Okay, the outlook will be just one sentence, even I think it's hard to believe, but then I will be giving you the references for all this story here. Okay, the papers where all this kind of appears. Okay, so let me just start for real now. Let me see the time on it. Okay, so random matrix theory, basically, what the aim of random matrix theory, it's a very old subject, which has now a very rich history, is to study the properties associated to matrices whose entries are drawn randomly from various probability distributions. At the practical level, unless you do numerics, you don't work with explicit matrices with, let's say, entries and so on. We'll explain how the formalism works. What are these properties? Basically, the statistics of the matrix eigenvalues. The eigenvalues are random variables, and as we will see in the next slide, we will be mostly dealing with what is known as a joint probability distribution function of the eigenvalues of a random matrix ensemble. So this is a very, so we will be dealing with n eigenvalues, which are random variables, and they are heavily correlated between them, okay? But let me just go to the definitions. This goes back to Bigner and Mehta and Dyson. It has a very nice history, the subject. Okay, this is the mathematical physics point of view, but it was studied in the 28 by Muirhead and statistical multivariate statistics. And for those of you who are interested in the genesis of the subject, there is a nice paper in the archive by Diaconis and Forrester that trace back random matrix ideas to the work of Hurwitz. Because you can approach the subject from many points of views, and if you study a bit Lie group theory, representation theory, you see aspects of random matrix theory there as well. Of course, that would be, this is a subject for a course, actually. But to fix ideas, I'm going to be thinking about square and Bayer matrices with randomly distributed elements. And then I have a probability distribution in this matrix space. This DM is the Lebesgue measure. And then, okay, this is very abstract, and I will be passing to the space of eigenvalues in the next slide. Also, Samir mentioned about that in the unitary case in his talk very briefly. And one of the most studied ensembles are Gaussian ensembles when the potential is quadratic. If you choose this Gaussian behavior, you have extra properties in your random matrix ensemble. I will be talking about this in the next slide. This extra property is that you have a statistical independence of the matrix elements. If you relax this property, then you can have invariant ensembles. I will be mentioning what I mean by invariant ensembles in the same way, but without independence. And then you can just study any other potential. So non-Gaussian ensembles is a huge topic. Most of the models I will be talking are non-Gaussian. And they appear if we relax this extra requirement that the matrix elements are statistically independent. If you want full statistical independence of your random variables, and then they have to be Gaussians. And then you can just put it in MATLAB and just have matrices n by n and choose that the entries are distributed among Gaussians. And everything that I can do analytically, you will find it in that way. But with other ensemble which are not Gaussians, this correspondence will not hold. Okay. This beta here refers to the symmetry of the matrix M, whether it's Hermitian, real symmetric. Okay, let me talk about that. So the two conditions are what is an invariant random matrix ensemble. So I need two conditions. The main one is the first one because it applies to any ensemble. So this probability is invariant under a transformation with another matrix, this matrix U, and this U is either an orthogonal, this is beta 1, unitary or symplectic matrix. This is depending whether M is a real symmetric for beta 1, Hermitian matrix for beta 2, or quaternionic self-dual for the symplectic symmetric case, beta equal 4. Okay, so what I am demanding for the ensembles to satisfy is this property here, this invariance. So this is why they are called invariant ensembles. If on top of this condition, I impose this statistical independence between the entries of the matrix, and then it's the only case where I have this kind of description between the probabilities I'm going to be talking about all the time and explicit matrices n by n with uncorrelated entries, then necessarily the potential has to be Gaussian. So these are the Gaussian. So a most famous one is for beta 2 Hermitian matrices. It's called the GUE, Gaussian unitary ensemble. For this other is the GOE, Gaussian orthogonal ensemble. For beta 4 is the GSE, the symplectic, the Gaussian symplectic ensemble. Okay, but this is a bit theoretical, not yet useful fully. And okay, Samir already mentioned this in a much more effective way than me, much quicker for sure. There is a diagonalization property. You can pass from the space of matrices to the space of eigenvalues. This means that you don't care at all about the eigenvectors. You are integrating out all the eigenvector information. This is very typical in random matrix theory. You can also study this is much less developed subject. People in condensed matter are interested. You can study but you have to do, typically you have to do numerics. You can study this behavior of the eigenvector sector, but we don't do that, okay? So the price to pay for this in this transformation is, as was mentioned already, the Jacobian of the transformation. And then the symmetry of your matrix shows in this correlation term through this beta parameter that I was mentioning. And remember, this is beta 1 to 4. This is the Dyson paradigm. It's called the threefold way, Dyson's threefold way. This has been vastly extended. And you have also beta ensembles where beta can move freely. And then, well, this is way more recent. And there are also generalizations that the threefold way is just a particular case. You have ensembles which are related to the Cartan classification of Riemannian symmetric spaces, and you can have many other, if you go into this, and this has become very, very popular right now with topological insulators. It was already before. This is work by Adland and Zimbauer. I'm not going to discuss anything at all of that because it's a wall in itself. But what I'm trying to say is this is not the whole story. It's the initial story, it's the Dyson story, if you wish. And it's more than enough for me because all the models, actually, the models I will be talking about and all the formalism I will be discussing is especially simple in the specific case where beta is equal to 2. So not only I'm restrained to this paradigm, but I'm just even only moving in the beta equal to 1. This is for Hermitian matrices, basically, or unitary matrices. When you have beta 2, this van der Mondes square, you have a very powerful formalism, which is the classical random matrix formalism. In random matrix theory, you're interested in what? You're interested in what in statistics called the marginals, the integration of this, because this is a much more concrete object, but it's an n-dimensional. This is the joint probability distribution function. So it's an n-dimensional correlated distribution of random variables, right? So you want to study integrations of this, and you study partial integrations. Normally, you are interested in 3 of them. The one very obvious is to integrate the whole thing, right? And then you integrate the whole thing, and then you compute the normalization constant of your distribution. Okay, this is the simplest you can do, and this is what I've been done the most. It's not so simple to do that for every n. And for example, for this, all the classical prototypical model, the gross-Witten model, which is from the 80, there is no exact formula for finite n for this Cn, which is the partition function of the model. And for large n, yeah, it's extremely simple. It has like a Gaussian shape. But I will be explaining why. So for a very and then there are models which are seemingly more difficult. For example, Chen-Simons models, where this is fully solvable. It's fully solvable, of course, for Gaussian ensembles. But even this thing here, which from the probabilistic point of view is just the normalization constant, can be hard to compute explicitly for every n. For large n, it's another story, and we will be talking more about the large n and with the scalings here in the potential. The other 2 quantities integrated over everything except 1, and then this is the density of states. So you have how the density of eigenvalues correlate distribute, if you ignore correlations. So if you have a Gaussian here, this is very famous. This is the Wigner semicircle law in the large n limit. And this is how the eigenvalues distribute, right? And then the other object is the 2-point correlation function, which when you this tells you local properties, because these are heavily correlated random variables. So the statistics of the eigenvalues, really, if you want to study the statistics of the eigenvalues, you really have to study this 2-point correlation function. And this is a very important subject in random matrix theory because it's related to the notion of universality. This universality means that you can choose a number of potentials here and maybe have certain scalings, and there is a whole host of models whose correlations are the same. And they are in the Gaussian universality class. This doesn't happen for the rho. The rho is a global quantity and it's not universal. But the correlation function is a local quantity and so a whole lot of interest has been devoted to study universality classes in random matrix theory, meaning the interactions between the eigenvalues. This has become also prominent in gauge theory in the recent times because of the introduction of the quantum chaos ideas in the study of black hole physics, etc. So typically in gauge theory, applications were more based on computing partition functions. This means this object here. And in recent times, studying correlations of spectral form factors, etc., it has moved more into the applications that were also prominent in condensed matter, which is the correlations between eigenvalues. Okay, I was mentioning that this is what actually the setting that Samir was talking about, basically in his talk. So this is why I was saying that you can study Lie group theory. And if you go do a bit of representation theory in Lie graph theory, you will find something very important, which is called the Well integration formula. And then you learn this fact thing, that when you have integrations of class functions on Lie groups, for example, the unitary group, you have this basically you can reduce integration to the maximal torus. Yeah? So one integration which is over UN, and this is the hard measure of the UN. You just have to integrate over U1 times n. Okay, so you can end up, and the gross-Witten model is a model of this type. Okay, so you can end up with finding random matrix theory in different ways. Okay, let me check the time. Okay, I'm going really slow. So for computing, this is a very powerful formalism developed mostly by Dyson, also Godin, Meta, and others in the 70s, 60s, 70s. Very powerful work because you can, it tells you if you know the orthogonal polynomials associated. Imagine this defines your model. Your potential defines your model. If it's a Gaussian, this e to the minus x squared. So you have a orthogonal polynomial systems associated to this weight function, which is a Gaussian, and the polynomials are the Hermite polynomials. So this is like when you solve the harmonic oscillator. If you know these polynomials, you can construct this kernel. This is called the two-point kernel, and it was shown that any correlation function. This is a powerful result because this is not just integration. This is any marginal. So you can look at 3 point, 4 point, which may be overkill. You can construct it as a determinant of this two-point kernel. And the two-point kernel itself is the two-point correlation function of this model. Okay? This property holds, maybe the order of presentation is not optimal because this is the first one and then this counts. But this kind of holds because this kernel has a reproducing property. So it's a reproducing kernel. Yeah? So for those of you who know, and because of this powerful reproducing property, this determinantal formula holds. Okay, this is an object which is central in many other areas, and in recent times, I'm looking more at this from the point of view of probably statistical machine learning, because this object, regardless of random matrix theory, appears a lot. It's very important, in fact, in statistics, because can be seen also as a delta sequence. So a sequence of functions, if you move the n, that reproduce the delta function in the n infinite limit. So for statistics, for multivariate statistics, it's an important object. What gives you random matrix extra? It gives you integral representations, because we know that this comes from integration of this type of distributions. So you can flip in random matrix theory. You want to study. You have these models, this type of models, and then you may want to study compute the z, the cn, the rho, or the kernel. For other areas where this is the object of interest, you can flip the script a little bit and try to use the integral representation. For example, using character expansions that were also mentioned in the first talk on Monday. And obtain other quantities. Okay, so this is something I'm looking into, but if anybody's interested, I would love to talk about that, but it's not the subject of the talk. And this is a very powerful and very useful identity. You don't need to do the sum, is the Christoffel-Darboux identity. This is one-to-one with the polynomial satisfy a three-term recurrence relation. So this is very easy to prove. I mean, if you take into account that this satisfies a three-term recurrence relation, and you apply it here, you will see that this sum is telescopes, and you cancel all the terms except the first and the last one, and you end up with this formula, which is extremely powerful. Why this is powerful? Because for large n, you don't need to do the sum of infinite terms, but you just need to use the asymptotics of the polynomials. And this is how, for example, you can obtain the semicircle law, or the famous sine kernel, which now appears very much in the studies of the spectral form factor. The sine kernel appears using this formula and using the asymptotics of the Hermite polynomials with the proper scaling for large n limit. So you use this, not this. And if you do Hermite with the asymptotics, the Planck-Erel-Roth asymptotics of the polynomials, in the large n limit, you end up with a proper scaling of the variables, which I'm not writing here. You end up with a famous sine kernel, okay? And you can study universality using this. Okay, let me move on because this is, maybe I'm going a bit slow. What else is interesting? You can relate all these integrations, all these multidimensional integrations to the theory of matrices. So then this is useful. Why? Because if you have an identity between two different objects, every single one of them comes from a different area. This is more from linear algebra or other areas, and they have their own tools. So you can sometimes apply or cross every area has their own tools, so it's useful to have different equivalent representations. So what is this? This is a typelet matrix, which is just a matrix with constant along diagonals. What are these constants? These constants are the Fourier coefficients of a certain function in the complex plane on the unit circle, which is called the symbol. Okay, and this is the determinant. This type of matrix appear in many physics problems. For example, can be the Hamiltonian of a translation invariant system, and then you have a Teplitz. What is interesting, there is this Andreev identity, which also has this name for this specific case, the Heinz-Theo identity, which tells you that this determinant is equal to a unitary random, the partition function of the unitary random matrix ensemble, of a matrix ensemble which was of this type that I was mentioning here. This. Yeah. The ones that also Samir was talking about a little bit, although he had a different structure. And then you have the van der Monde determinant, and this F. So the Fourier coefficients of the function in my matrix model, this is called the weight function in the random matrix letter. The coefficients here are the entries of the matrix. Okay. So that's one of the nice connection, which is useful for many things. One is the Sego theorem, but I don't have time. And way less known, because this goes back to this is more than 100 years old, but this is way more recent in many ways, is that you can strike columns and rows of your Teplitz matrix and compute the determinant. This is a minor of the original matrix. Of course, after doing that, the resulting matrix is no longer Teplitz unless you strike in a very simple pattern, like for example this and this. But for this striking, obviously in general, it's not Teplitz. It's not Teplitz anymore. So, but still, in this striking, you can show that any striking of row of column, it can be encoded in two partitions. Okay, so you have this notation. Now we are not studying the determinant. The Teplitz determinant is J minus K. But now we have this kind of partition. So any striking pattern that you want, you have two Young tableaus that decorate your determinant and characterize fully this striking pattern. So this striking pattern, for example, corresponds to having just one box and 2 and 1. Okay. What is nice about that? What is nice is that the random matrix description still holds, but now in this matrix integration, we have the insertion of two characters, which are the Schur polynomials. Each one of them encoding the partition character in the representation that encodes the striking pattern that I was alluding before. Why is this relevant in gauge theory? Because in gauge theory, when you do localization, for example, of supersymmetric gauge theory, when you study the partition function and you do localization, you end up with a matrix model maybe of this type, but without the Schurs. But if you study the Wilson loop, this is just one way it's interesting. When you study the Wilson loop, you at least have one insertion of a one. Of course, if you only have one insertion, it's a more restricted, but it's also a minor, of course, but it's a more restricted striking pattern. In Chen-Simon's theory, these two corresponds to the case of having to study a Hopf link. So you have, for example, 2 1 knots with a non-trivial link. So this is called the Hopf link, right? And it will be described with this object, for example. Okay. I will be alluding a little bit on this determinant notation, but let me just move on because okay. So what type of matrix models we can study? So let's just reminisce a little bit about the late 70s, early 80s, where a lot of papers were in this subject, which was studying 2D Young-Mills theory. This is also called the one-plaquette model. And then if you study this 2D Young-Mills on the plane, you only need to study one plaquette, and it reproduces everything. And if you study this plaquette in the lattice gauge theory version, you put the Wilson lattice action. This is what Wadia and Gross and Witten did. You end up, this is the trace of U mass plus trace U dagger. So this is the cosine. So this is the Wilson lattice action. And then they found that the partition function of the model, this one plaquette model, was given by this matrix model. So up to now, I was talking very much about computing these integrals, but what we find in this paper by Gross and Witten, and this kind of phase transition wasn't, now is something very well known, but if you look at even the title of the paper, it says like possible third order phase transition. So it was really not as clear, and then many papers later on came out using other lattice actions like hit kernel or Manton action, many other lattice actions that reproduce the continuum field strength tensor in the right way. But what they found is the following: that you study large n, and then you only have the coupling constant. This is the coupling constant in your Lagrangian, this G, and then you take this product of n and fixed. And they found that for there is a phase transition of third order, so you have two functions to describe the partition function for the whole lambda. And you have a big weak coupling phase and a strong coupling phase. If you study, you can also study Wilson loops, and you will see this kind of thing as well. And then, like I was saying, you can study with the same theory with not exactly the same theory, because this was for compact Riemann surfaces. And then some people decided to look into the hit kernel lattice action because, in the weak coupling limit, they go to the same thing, of course, but it had nicer properties. So if you choose this order based on the diffusion equation, on the heat equation, then you have, Migdal formula is from 75, so it's from older than this. But maybe I should have written here in the matrix model form, because, okay, I'm going to mention about that. And then you have this kind of sum of representations. These are the lambdas I was writing before, and these are representations of the unitary group. Okay, so this is related, again, well, I think I'm going to say the word Samir more than matrix models many times, but he was talking about random partitions. This is very much related to random partitions as well. So this is can be understood from that point of view. But for our talk, more interestingly, you can attach a matrix model of the type I was mentioning before to this expression. So I have not written here, but this is totally equivalent to a Gaussian ensemble, unitary ensemble, with the eigenvalues discretized on the real line. How do you find that? You can write these dimensions explicitly in terms of the boxes of your Young tableau. So you have both the dimensions of the representation and the Casimir have a totally explicit formula for in terms of the lambda and mu sub j, right? The boxes on your Ferrez diagram, your Young tableau. So this is called the well dimension formula. Okay, when you do that and you just do a change of variables, just a shift, you have that these variables, these boxes of your Young tableau are the variables, and you have these sums. So this is like, for those of you who know random matrix theory, this is a Gaussian model where instead of integrating over this is the Gaussian weight, and this is the van der Monde square. Okay, so it's a model of this type. Let me I hope this is not very annoying. It's exactly a model of this type where this is a quadratic. So these x are are integers because they denote the boxes on your Young tableaus, and you sum over all the possibilities. So instead of integrating, you have to sum. So it's a discretization of this type of density. So this is not obvious, but this Migdal formula is a discrete matrix model on the real line of the Gaussian type. Okay? Also Hermitian because we have here a square. And this is a square because it's a sphere. So this holds for the sphere. Okay.
Sorry, Miguel, can I ask a question, please?
Yes, Samir, go ahead.
Yeah. Hey, there is also a way to write this as really as a continuous integral, right?
Yes, but you have, that's an important point actually, because this has to do with the phase transition. I mean, the discrete model is genuinely different from, for example, this discrete model is the one that has the phase transition, which is because a GUE doesn't have actually the partition function of the GUE is the volume of the unitary group. It's a G-Vans function. So this is, even if you do a scaling, you don't find any. So the weak coupling phase of this discrete model is the one such that you can describe the model, this discrete, in the continuum version.
And what is the action of that model?
The action, it's quadratic action.
I see. Even in the continuum.
Yeah. So what I'm saying is that the continuum, I don't know if we're thinking about the same thing, but the continuum, at least in the larger limit with double scaling, is the one that describes nicely the weak coupling phase, and is the one where you still don't have instant. I will be talking more about that. But it's an interesting point because this discretization is what makes the phase transition to emerge. And analytically, for finite n, this is very hard. Because typically sums are harder to compute than integrals, and the same happens here. You can do with Hermite polynomials in the continuum case. You cannot do it. So the discrete version of the Hermite polynomials, it's a complicated thing. So you cannot do it. So the continuum description only holds for a certain region, at least when you go to large n. Okay, so this means that the integral is describable. If you want to flip the argument, the integral, it's only describable through sums. And this is what people do in numerical analysis, no? Numerically, only in a certain region. But I'm going to talk more about that because this is related to the main thing on phase transitions. So the point is that in '93, then Douglas Kazakov showed that this guy here, also in a double scaling limit, has a phase transition. It's also third order. So again, we find the third order, this kind of exotic order outside of random matrix theory for both. The underlying mechanism is very different, and maybe I won't have time to explain fully. This is also related to arguments that Samir was giving in his case. But for the, let me just go quickly through it. I mean, normally, for example, in the how do you see it in the unitary? In the unitary matrix model at Gross-Witten, the signal of a phase transition is the opening of a gap. Because it's a compact support, the eigenvalues have compact support. This means that the density, the separation of the eigenvalues has a maximum, right? Basically, this translated to the density of states gives a lower bound to the density of states, meaning that the density of states has to be bigger than zero. Okay. When the support of your distribution, when you study this large n with the saddle point equation, you just go into the column picture. I'm not sure I will be able to be more specific about that, but maybe if there are questions, we can talk about that. When the support of your distribution hits this lower value, then there is this opening of the gap, and then you have this other phase. So this is, and then you sometimes talk about the weak coupling phase and strong coupling phase. And this phase transition is kind of canonical. It has appeared in many works later on, because even if you put more interactions here in your potential, this is the potential in the cosine, you have cosine of 2 to phi, etc. You still have third order phase transition. Okay, and we kind of discuss that even with infinitely many interactions in the potential, you still have this third order phase transition. Okay. So this is one mechanism here. The mechanism for this other guy is very different. It's because of the discreteness, because now we're living on the real line. So the discreteness gives you something different. It gives you that the distance has a minimum. So this actually, for the density of the states, gives an upper bound. The density of the states always has to be smaller or equal than 1. So the underlying mechanism in the matrix model is very different, just because of the topology of the space of where the eigenvalues live. Okay, so okay, let me see time-wise. Okay, I think okay, I'll go a bit quickly through this. One thing that we show in this paper, which was also a bit inspired by statistical mechanical problems, is that okay, let's look at a case where we can kind of try, if we have, for example, a unitary matrix model, try to see equivalent on the real line and see how the phases go. So you can do the stereographic projection. And at first I thought we were doing okay with this because it's a mapping which is one-to-one. This is the Cayley transform. Is what you also do when you pass through a scattering description to a Hamiltonian description if you want. But due to this, the North Pole goes to plus infinity, minus infinity. And perhaps because of this, what we could find is that for finite n, when you do this, this is maybe not the most interesting part, so I'll go a bit quickly through that. But when we studied matrix models, doing, for example, this change of variables and trying to study, we obtain, and possibly the culprit is this kind of point, this puncture on the circle, that at finite n, without scaling, the models coincide because they are finite integrals. You do a change of variables, you can do the integral in 2 different ways, which in some models we could. It has to be the same, right? But for double scaling limits, that was not the case. And typically in the unitary matrix model, we found a richer phase structure. And then with Jorge Russo, more recently, we studied a generalized Gauss-Witten, actually, is this model where we also have a cosine, but in the here in the outside the exponential, I mean, like in the integrand. And this kind of changed a lot. And this model can also be mapped into a model that Jorge had studied previously, also this summer, on the real line. And again, we found out that the phase structure in the unitary model was way richer. Actually, only doing this deformation to the Gaussian, if you look at this paper, you see they have a very complicated phase diagram. We didn't fully study the phase diagram in this case, and we even have some smoothing of transitions. So it's a very surprisingly simple model, or a model which is apparently simply surprising complicated phase structure. So this is one way of seeing that you have to be careful on what type of matrix model you are dealing with. Another way is the following in this paper, where we show actually that these two models are equivalent in a certain way, in the sense that they give the same partition function for finite n. But again, the same thing happens, that if M1 is different than M2, and I will explain a little bit why, the phases were different. Okay. This actually, we did this. The difference between this case and the previous one is that we don't, to go from this to this, we didn't do any change of variables. As you see, no change of variables seems very, very feasible here, because not only this is on the real line, this is on the unit circle, and this is on the real line, but this is continuum and this is discrete. So there is something more than just a change of variables, right? This we did with random partitions, because these guys both have you can write it in this form, in this Migdal formula form, but without the quadratic Casimir. So when you have this type of expression, you can attach always a discrete random matrix model. And this is been hugely developed in mathematics, Johansson and many other people, because in probability theory, it's a big topic. But this is what I was saying to the young Mills. This is a discrete Gaussian ensemble, because you can always attach, like with a well-dimensional formula. If you don't have a Casimir, or you have a linear term here instead of quadratic, there are some identities which I cannot go into that prove that this is a Teplitz determinant. But this only happens in this simplified case. Because if you remember, I told you that Teplitz determinant is a unitary matrix model. This is how we end up with this equivalence, because both of these guys have the same sum over representation description. So my motivation here was that some people studied in a dimer problem. They have a classical two-dimer problem, and they had a corner on the left, upper left part of and that developed a third order phase transition. So they had this kind of, this is called a Meixner ensemble, because this is a linear, you see the potential here is linear, it's not quadratic. This is why we can do all that. So they found a third order phase transition. And what I was saying to Leo is that I knew this Teplitz connection. So I was telling him that because this kind of generated quite interest in the statistical mechanics, this kind of phase transition in this dimer problem with this kind of corner cut into your lattice, that you could do it with a unitary matrix model. And I expected to be completely equivalent, because what I'm saying. But we found that it's only fully equivalent if these two coefficients are the same. I'll explain why. Now, so for finite n, they are. But when they are not equivalent is when you study. So moral of the story is that you have to be very careful with if you have equivalent matrix model description and you want to study phase structure, the scale limits, you have to be careful. So we obtain with this.
Sorry, can I ask a question? So,
yeah, Samir, go ahead.
Maybe it's me, Samir. Actually, this was the question I was asking. So for the two models that you showed earlier, like the Gauss-Witten Vadia and the one studied by Douglas and Kazakov. So are there equivalent statements for either of these two models? That's what I meant by unitary description. So is there a unitary description for equation one in this sense that you just showed?
Very good question. Yeah, but not with this structure. I think there is a paper by, there's a paper by Menotti and Onofri from 1980 or 81, where they actually they were one of the first after Migdal that they studied the heat kernel lattice action. Well, as you are saying, the phase transition they only look later on, like 13 years later, Douglas and Kazakov. But because I think the thing went, this was a bit surprising. Now it's very well accepted. So people were trying other lattice actions. So, and then they kind of, if you try to write it in a unitary way, it's you have like it's like vortex contributions. It's a complicated. So it's not, because this is like a description where you have a description on the maximal torus of your unitary group. Maybe it's more similar to the setting that you had, because what I'm trying to say is that you have, yes, you have like a two-body term which is more complicated than this, but this is what you had, right, in your talk also, so yes, you can do it in this form, but it's not very tractable because of this thing. It's if you write the heat kernel lattice action in these other variables, the price to pay is that you don't have a standard hard measure. You have it's like a very causeless type of formula where you have you can interpret as vortices. It's very interesting, but I don't think much has been done with that because it's very hard to analyze.
Yeah, so thank you. And what's this reference you said again, please?
I think it's a nuclear physics B of 1980. You'll have it's very clear paper. You have the formula right written there. So I'll send you the reference if you want. So or either physics letters B or nuclear physics. Okay, I think I cannot go out of this system.
No, don't worry, please.
Okay, I'll send you later. It's very yes. So you have like a non-abelian term there, which is complicated. But yeah, it's possible. It's possible, and I don't know. It's been very much analyzed, but you have it explicitly there. A unitary version of the heat kernel. Okay, so what we found is that in this model here, okay, I was pointing with a finger, don't do that. Okay, we obtain that if these two parameters are equal, we obtain that the order was decreased to second order, because you see that the third order was like very robust up to now. And this, if you think about matrices, you remember the Teplitz description. This is the determinant of a band matrix, a banded matrix of Teplitz form with these powers of t in the entry. So this has been studied from very different angles, because this is a banded Teplitz matrix, and this M1 M2 is if you see this is a Laurent polynomial in Z in the variable. It stops being symmetric if these are not the same. So if it's a symmetric, so you have this symmetry of this inversion over the Z can be inverted to 1 over Z, you have a second order phase transition, but not if they are different. So you have, okay, it's abstraction. So we have explained in the paper, but maybe that's a bit technical, is that the unitary matrix model becomes complex in this case here, okay, because of this thing I just explained, because this asymmetry basically. And this is very innocently looking from the matrix point of view. From the matrix point of view, Teplitz matrix point of view, this is very simple. It's a banded matrix, but we have to distinguish between the entries of the matrix, if you expand this polynomial here, and the terms in the potential. Okay, I think I have some chat here, maybe, or I don't know. Yeah, Menotti and Onofre. Yeah, Jorge, George. Yeah, exactly. Yes. Sorry, I was okay. So I was looking into the chat because when I was teaching classes, I was looking at the chat all the time. Okay. So what I'm trying to say is that this is seemingly this is way more complicated in many ways than the Gross-Witten, in the sense that if you write with the exponential of something, the potential, we have logarithm in the potential. So this has logarithmic potentials actually. So we have infinitely many interactions. So I think I cannot go through this because I think I'm totally out of time. But we explain in the paper here with Leo that if you can deform the contour such that this deformation of the unitary circle still leaves the potential being real, then we are fine. It's still third order. But if not, then it was. Or I say it conversely. Then it's second order. I said if not, it's second order. Okay, so and this is because it's a logarithm. The potential is a logarithm. If it was the Gross-Witten with additional terms, then it would be fine. we can kind of find this new contour. Okay, so this is a bit of complex analysis interpretation there, just deforming the contour. If you can look it in the section 2.6 in this, and I think we explained it there with some detail, because we were curious. So this is the lesson we learned, that always agree at finite n, but only at large n, and then this real valued property of the potential in the unitary case. Okay, which this is not in general well known, I think. So we didn't know that. Okay, I think I'm not going to have much time because I'm almost out of time and I don't want to harass you. But let me just say very briefly. Possibly this is something that people know better or well, because there have been a flurry of papers on this TT deformation. Let me just mention that I don't know if Ricardo is here also, because Ricardo is one of the co-authors of these papers. He's in Lisboa for a few months as a postdoc, Ricardo Conti here. So please ask Leo and Ricardo here. They are very bored with the epidemic and so on in Lisbon. So they, with Roberto, Tateo, and co-authors, they had a very nice, well, they studied several theories, but then they look into the 2D Young-Mills theory on a Riemann surface. And this kind of TT deformation has a flow equation for the Lagrangian, when you have the derivative of the Lagrangian over the parameter, you have one parameter tau in this TT deformation, is equal to the determinant of the tensor energy momentum, basically. And if you solve this, they solve perturbatively this flow equation for the Lagrangian, with the initial condition being the, well, the first study, the Maxwell theory, but then they generalized to the non-abelian. And only in 2D Young-Mills they could give, as far as I know, they could give it analytically. And it's very complicated. It's hypergeometric for the Lagrangian. So the Lagrangian has hypergeometric form, which is very scary. But they managed to introduce the conjugate momenta, and they did the Legendre transform. So they managed to obtain exactly the Hamiltonian formulation. And very surprisingly, the Hamiltonian is way simpler. Way simpler. What happened in this the Young-Mills case? That the result was that now I'm going very quickly, but this was already told. Yeah? This for the sphere, this is the genus of the Riemann surface zero, so this is square. So they obtained, in the same story I was talking up to now, they obtained this deformation of the Casimir. So the Casimir is now the form which had not appeared, because there's been many deformations, generalizations of 2D Young-Mills theory, Q deformation, generalized Young-Mills theory. In the Q deformation, you had quantum dimensions here. This is very much related to Chen-Simon's theory, etc., and topological strings. Another, you had higher order Casimirs, but this had not appeared. And they checked that this has nice properties. This partition function with this deformation satisfy a heat equation, where the time variable was this tau, and the space variable was like the area of, this is the area, which is the only parameter you have into the Young-Mills. And this was same type of relation that the other works on TT deformation by Cardi, Young, many others had appeared. So they found consistency there. What we did is to redo the whole Douglas-Kazakov story for this kind of perversion of the Casimir, which is not trivial. We mostly do work perturbatively. And Leo has given it, so the saddle point equations, basically, this is the thing that I was mentioning before that gives you the phase transition in any case, because you have this bound on the density of states. And then in this model is different. You have, it's not an opening of a gap, but you have one solution, which is the one cut, and then you have a two cut solution and a saturation region in between when rho is equal to 1. So with Leo, we redid it's Douglas-Kazakov paper, but with this, and then we did a geometric expansion of that term. So basically, what we obtain is that. Let me just tell you the result, because otherwise, I'm giving the link of there is a YouTube talk by Leo on slides that he just talked only about specifically about this. The result, what was the result? That the phase transition remained the same, was still third order, and the critical area, the area where this occurs, was lower. And we will explain a bit why. Then we also find another thing, that there was a maximum tau, which is the deformation of the TT deformation, where the weak phase completely disappeared. This is because the instantons, this phase transition is well known to be generated by instantons. This is work by Gross and Matitzin. So we studied the suppression factors of the instantons. I'm going to be showing In the next slide, this is the third order phase transition is the same. Let me just show you, because this is a bit related to what Samir was saying. As you can see, okay, this is the suppression factor. We started from this instanton point of view. You can rewrite the partition function with Poisson resummation only, and these are instanton contributions. And what we found is that they are less suppressed, basically, and the higher the tau, sorry, the less suppressed they are, until at one point they are not suppressed at all, and there is only strong coupling phase. So we not only find the lowering of the critical area, the order was the same, third order, and then the instanton contribution was characterized as well. It's less suppressive. So meaning this is why it lowers the area, because for the same area they are less suppressed, so they are stronger earlier. This is the instanton contribution. So this is what we found is that the gamma. This is in the gross matrixing paper, which followed the Douglas-Kazakov work and had this instanton point of view. The gamma we obtained for the TT deforming is the same. The only thing is that it's rescaled in this way. So basically, okay, you can see here, but with the instanton picture, you can find consistency with all the properties we obtain. So you can apply the random matrix tools to this TT deformation, even if your potential has been grossly deformed. Okay, so okay, this is what I just say with words, and I'm just finishing. Let me give you the references because I think we're out of time. So okay, that was really rushed at the end, but the conclusion is this: that you can study phase transitions with matrix models in a double scaling limit. It's very useful, the matrix model technology, and these are the references. So for the TT deform, where is it? Is this one here, and then this is taking Douglas-Kazakov for the Conti, Tateo, Negro deformation of the 2D Young-Mills theory with the TT deformation, and this the 2D Young-Mills is deformed. So we did the deformation of a deformation, if you wish. This Q Young-Mills is related to many other things. We kind of the same results that we obtained here, we kind of did here, and a few more things, like the factorization properties of the Hilbert space of your 2D Young-Mills theory does not hold any longer. You lose a lot of things. For example, there is a connection of Chen-Simon's theory between this theory. You don't have it anymore with the TT deformation, but there was no time. So, but ask Leonardo. He's very bored. Only has to deal with me. So, okay, I think I'll stop here. This is the hour. Thank you very much.
Thanks, Miguel. Thanks very much. Are there any questions?
Yeah, I would like to ask, can you, since nobody else is asking,
yes, I mean,
can you just expand on the very last thing you say? It was very interesting. So the usual Q deformed Young-Mills theory has some, when you write out the partition function, there's a relationship to Chen-Simon's theory.
Yes.
So what happens to that under this deformation?
Leo, can you explain this? Leo, come on. We agreed that you would talk about the Q deformation. I want you to intervene.
Yeah, if I may, yeah, the point is that well, the connection is more properly with the Wess-Domino-Witten model, but which is CFT, but the TT deformation moves you away from the conformal fixed point. So essentially, many of the properties you have, you lose them because of you first TT deform, and so yes, that's the point. We also tried to check whether we could first TT deform the Wess-Domino-Witten and then gauge it, or the converse, and they give completely different results. So this is at a practical level the reason.
But I guess the question is there a statement? I mean, naively one could have imagined that there is also deformation of Chen-Simon's theory, which that maps to.
Yes.
Is the statement that there is no such thing, or?
Yeah, exactly. This is one of the questions I was asking Leo, and that I was, because also there is some people studied who was Bonelli, and Bonelli at least, that he studied the TT deformation of Wess-Domino-Witten model. So because you have this holographic relations between Chern-Simons and Weston-Minot with the model, I thought maybe, but we look into that, and well, that was, he did it classically. So I think there is no, we couldn't find a way. So this is one of the, a lot of questions that I asked Leonardo about that, and well, he mostly looked into that, and he couldn't find a way to, but yeah, that's a very interesting question because it was one of the objectives, and it has to do also with the, maybe Leo, you can comment on that, on the fact that the when you have the sum of representations and you write everything in terms of the S and the T matrix, the fact that the sum doesn't truncate anymore because this happens when Q is root of unity. No, this was the
yeah.
Okay, so maybe you can.
Yes. Also, the connection with Chern-Simons theory is that you have the Q in Q deformed Yang-Mills is not a root of unity, and it reduces to Chern-Simons partition functions when you take Q to 2 pi I over K with K the Chern-Simons level, because you have this the sum of representation. You can write it over matrices which reduce to the modular matrices S and T at Q root of unity. You don't have this property anymore after the TTD deformation. So maybe also one thing that can answer your question is that we know, well, we do not have a clear understanding of what is the TT deformation of higher dimensional theories. And there have been some attempts to understand the deformation of CFTs in higher dimensions, but maybe using ADS CFT correspondence. But well, for Yang-Mills theory, it's not clear, at least at the present stage, I think.
I had another question. So maybe you said this, but you said it a little too fast. The Douglas Kazakov picture, there is of a physical picture of exchange of dominance of partitions. No, in one case the partition sort of goes fully, and the other one it stops and right now. Now when you tune, so now this TT bar deformation has some parameter. I don't know what you call it, tau or something like that.
Yeah, it's a tau parameter.
Yeah. Now what happens when you tune that close to one or the other limit, whichever it was, one or if you show me the model outside.
Yeah, I think the problem with this,
over ends when the denominator goes to 0. I mean,
yeah. I think I'm not sure if I'm certain on this, but I think with this picture that you're saying, I'm not sure in longer holds, because this picture that you're saying it's based on the fact that there is a factorization of the Hilbert space, right, between chiral and anti-chiral, right, and you can do that. One thing that we look into is that with the TT deformation, this is no longer the case.
That is broken. I see.
That's broken. That's one of the. So this kind of Fermi picture that you had that also Douglas discussed, and
that's right.
We have this explaining in the last paper, the one I didn't mention, that was with Richard. We have like a section on breakdown of factorization, and because in one theory. We cannot do this splitting that you are saying, which is very.
I see, but so just to continue,
there is no string picture as far as I know.
No. That's exactly why I'm asking. But just to continue, in this Douglas picture of fermionization, I mean, so in that case there is some relativistic fermion, a certain dispersion relation that is relativistic fermion, so that the chiral and the anti-chiral are separated. I mean, can one imagine sort of deforming that these fermion, that there's still a fermion picture, but not relativistic anymore?
I don't know that we just, that's another question that actually was asked, but we couldn't solve actually. But because we saw this kind of breakdown of factorization, we didn't go further into that. So you mean what happens in the fermion picture with the deformation, basically? It's like,
I mean, the fermion picture per se holds. No, it's only the dispersion relation that changes.
I think maybe it has to do with entanglement. Now there is some kind of tricky entanglement there that no, Leo, you also kind of added some commentary on that, no? I mean, on this we had kind of
yes, the fact is that this matrix model, because of the C2, the Casimir in the denominator, well, if you think of it as a geometric series or whatever, you have non-local interaction in the end. You can map it to a fermion system, and then you have non-local interaction. So that's what was a bit confusing for us. So, yeah, you can try, but we couldn't find any dispersion relation or any simple relation anyway.
Okay, thanks.
Thanks to you.
Okay, any other question? So if not, let's thank Miguel again. And Miguel, I would like to ask you to exit the share screen.
Okay, no, I'm staying here. I'm not, I don't want to leave. No. Thank you very much. See you later. Let me just, what is it? Live here. Okay.
So Ricardo.
I'm here.
Hi there.
How are you?
So, okay. Could you then share the screen?
Am I allowed? Okay.
Yeah. Thanks.
Wait, I have to go full screen first. Give me a sec.
Hi, Ricardo.
Hey, what's up? I think it's like this. Let's try now. Is it working?
Yes.
And you can see the little.
Yeah,
yes,
it's working.
yes.
Thanks very much. Okay, 2 minutes.
Sure, why not?
Okay. So next speaker is Ricardo Schiappa from the University of Lisbon, IST. And Ricardo will be talking about resurgent Pauli equations and two-dimensional quantum gravity. So please go ahead.
Okay, thank you. Thanks for inviting me. Pleasure to be here at home giving this talk. So I won't be talking a lot about black holes as for this talk, but I will tell something about the structure of 2D quantum gravity, I hope. Okay, so the slides, okay, they're working. So I'm going to be talking about work, which is basically everything is upcoming and some stuff is still in progress with a lot of people. So what's the idea? So the idea is how to get a grasp of non-perturbative structures in string theory, and I'll be focusing properly on 2D quantum gravity. So everybody knows that string theory is generically defined perturbatively as the standard genus expansion. You have here sum over Riemann surfaces. And you could ask, how can I obtain a non-perturbative definition, or for what I'll be talking about, and hopefully that will be slightly clear as we come along, a non-perturbative construction of string theory, which is slightly different from a definition. And we'd like to have such a construction in such a way that we also get the semi-classical decoding of this non-perturbative answer. By that, I mean that, we know what perturbative degrees of freedom are, things that go in GS, strings, whatever. And we would also like to have a decoding of what type of non-perturbative structures come in, exponential of -1 over GS, D-branes, whatever, and when they're relevant and when they're not relevant. So possibly one of the simplest examples is 2D quantum gravity. And by here, be more precise that in a second, but by 2D here, I mean 2D on the world sheet. And this is described by the Ponleville-1 equation. So let's look at that. Here, that's the Ponleville-1 equation. And that describes the specific heat of minimal strength theory. That is minimal CFT with C=0 matter, coupled to Liouville gravity. This was well known in the 90s. And so that's what I mean by 2D. For the moment, I'll mean something else in 2 or 3 slides. 2D on the world sheet. So what, I mean, this is nonlinear equation, so this is hard to solve. So what would you try to do? You try to do a standard string theoretic expansion. So I mean, here what U is the specific heat of this minimal string. Z is the string coupling. You see here how Z relates to G string. The free energy is just given by standard formula to come from the specific heat back to the free energy and the partition function. And if you do this calculation, you find here a bunch of numbers. They're all rational. And if, I mean, I've just shown you here 3 or 4. But if you compute a lot of them, you can see that the perturbative series is asymptotic. This means that these coefficients grow factorially fast. And so basically the series is asymptotic. You cannot evaluate it to a number anyway. So what would you do? You would say, well, I would like to go beyond this perturbative expansion. What kind of things can I find beyond this perturbative expansion? Well, there's actually many things already, basically known 100 years ago for this equation. That's the classification of singularities of the solutions to this equation. So this equation first came up with Ponleville and much studied by Boutreau in the beginning of last century. And their concern was in finding, let's say, quote unquote, nonlinear special functions. So generalizing classical special functions of analysis that all satisfy linear differential equations. And the requirement, it's not like you write some random nonlinear OD and that's it. The requirement was that the only singularities you have are movable, which means that they depend on boundary data. So they're not fixed by the equation. You can look at it, it's perfectly regular. And they're just poles, in particular, double poles, only the one. And so there's a classification, so this is the Z complex plane. And there's sort of 5 pizza slices. There's a symmetry of the equation. And there's basically 3 classes of solutions. The so-called tritronqué solution, where you just have fields of poles in one of the pizza slices and basically have 5 possibilities. There are tronqué solutions where you can have 3 adjacent pizza slices. There's also a couple of them. And there's a general solution. And so you can ask, I mean, this is, in order to find these poles, you really have to go non-perturbative. The perturbative solution only sees the tritronqué solutions. You cannot see tronqué or general solutions. So you really need to go somewhere non-perturbative. And there's certainly non-perturbative structure here also from the physics, because remember that double poles, I'll be more precise about that in a second, but double poles of the specific heat are simple zeros of the partition function, so that's associated to phase transitions. And you could ask, what's the exact location of these double poles as function of the initial data? Well, that's a hard question because you kind of need to know, I mean, that's a hard question generically, but that's also a hard question starting from the perturbative series, because you need to know Stokes data for this equation or for any problem that you try to go non-perturbative in order to adventure yourself into this non-perturbative realm. So here what I'm plotting is not the Z plane no more. Now I'm plotting the Borel plane for the Z variable. And here this theta direction with these dots is sort of a Stokes direction. Right? So a direction where there are singularities on the Borel plane. And when I'm venturing around the space of couplings, here the space of G string, the complex plane of G string, I might have to cross such a Stokes direction in its Borel plane, which means that the left resummation here, the theta plus, is not equal to the right resummation, theta minus, because as I cross, I mean, this is clear from the picture, there's going to be a bunch of Hankel contours encircling each of the singularities. So I really need to, say that the left is equal to the right plus the sum of all these people. And associated to each singularity is not only, well, I'll be more specific about that in the following, is not only a logarithmic structure that gives you the branch cut, but there's also Stokes data. And in particular, this is a nonlinear problem. And actually, Stokes data is not a number or 2 numbers. It's an infinite set of transcendental numbers. So, even if you construct a perturbative series, you do your trans series, you're still not done until you have accessed all these Stokes data. Otherwise, you cannot really cross these things and find out what happens on the other side of the phase transition. It would also be very nice, that's what I'm saying here, to have a physical interpretation of poles and Stokes data. For the moment, we still don't have it, but at least we have managed to compute all Stokes data, which I'm happy about. it's not only in the double-scaled case of Ponlevin and all minimal strings that things can be done. We can also just move away from double scaling, move away from criticality, and look at matrix models. And so here I'm showing you the string equation of the quartic matrix model. And it's basically an analog of Ponlevin. This is, sometimes people call this discrete Ponlevin 1 because R is now the specific heat. It's the analog of U, and I can equally find F and Z for the quartic matrix model. And what I'm plotting here, and again, I will be more specific as we go on, just trying to motivate now for a second. What I'm plotting here are zeros of the partition function, so on the complex plane of the 't Hooft coupling. So you really are seeing different phases of the matrix model. Not from, I mean, it's easy to sort of see these different phases when you look at eigenvalue configurations and how multi-cut solutions organize themselves. Here I'm showing the same as zeros of the partition function. So it's a similar problem to this classification of Boutreau, and you'd also want to go non-perturbative in Z if you want to describe these things. Of course, you can then try to think I can do arbitrarily complicated things. I mean, I can find harder examples in the double-scaled case by looking, I mean, staying within the realm of one matrix models, which is what we're going to be doing. You can find sort of the non-unitary minimal strength theories. This is the minimal CFTs with classified by these two parameters, 2k minus 1 with the central charge. They can be found by the KDVRT. There's gazillions of papers on this story. I don't want to tell a lot about this except the following, which is that I also have string equations, which now are nonlinear ODEs of much higher order. So I mean, you see that if I truncate here, so beta and above are 0, I basically get only the 1. But if these guys are allowed, things get clearly a mess very quickly. The string genus expansion can be written down. I just wrote F0, not the rest, but they're all asymptotic. And then you can say, okay, the higher the K, the worse. So is K to infinity the hardest possible example I can construct? Well, not really. I mean, this was made clear in the last year or so. That there is another, well, I don't want to say simplest because it's sort of new, but maybe people would argue that it is, but this is a very simple example of 2D quantum gravity. And now by 2D, I mean 2D on space-time, not 2D on the world sheet. So it's just a different interpretation. Again, there's gazillion papers. I'm missing a lot for sure. Now in the spirit of open-close duality. And what's that? That's Jacques Teitelbaum 2D quantum gravity. So here's the action. So sort of the Einstein-Hilbert part is just sort of a Gauss-Bonnet part. It's quite trivial. It's topological. Just gives you a number. And so the non-triviality is here, but you see that the non-triviality is actually very trivial because this is linear in phi. So basically what we have, the equations of motion are r equals to -2. So that's the case of ADS. And then there's some boundary terms. Let's not worry about that for the moment. So the interesting thing here is that you would naively expect that by ADS-CFT that the duality would be to a particular quantum mechanical system, but that's not the case, as was shown a year and a half ago by Saad Shenker and Stanford. Actually, JT gravity is dual to a random ensemble of quantum mechanical systems, which is quite interesting. The string theoretic expansion, I'll show you, I'll talk about that later, is still asymptotic. I mean, this is given by the growth of Weil-Peterson volumes. This was already known a few years ago to Mirzakhani. So you can ask whether it's also resurgent or not. So, I mean, that's sort of the setting of 2D quantum gravity that I want to talk about. And so this is the outline of what I want to tell you. So I'll tell you a little bit about Ponlevin series, and there's quite a particularity of, we think it's a particularity of string theory examples in general, but certainly we have not proved that in general. I mean, this is a particularity of all the examples we've seen so far, that there's a characteristic of these models which is known as resonance, which is very fundamental for solving them. Then I'll talk about these, the poles, the partition function zeros, a little bit about matrix models, and JT graph. All right, so let's go back to the Ponlevin 1 equation I already showed you. There it is. So how am I going to compute? Do it perturbatively. So perturbatively, I put an ansatz at large Z. Recall that this is G string goes as up to some rational factor goes as 1 over Z. So this is a small gs, large Z expansion. And what I have to compute is those coefficients there. Those are numbers, right? There's no other parameters in here. So, I mean, I just put the ansatz in. There's a recursion equation. Here, I get these numbers 1 over 48, 49 over 4608, and so on. And they're asymptotic. Now, let's try to go non-perturbative. So this is second order differential equation. So that means that there are 2 instanton actions. This is not hard to see if you just put an ansatz with an exponential into it. And you're going to get an algebraic equation for A. which is actually gives you two symmetric roots, plus and minus, and that's at the root, in a different meaning, at the root of the fact that resonance is going to be at play, and that is always the case in this minimal strings matrix models and so on. So then you try to say, okay, I have these two instanton actions. Let me construct a trans-series solution. So what's the trans-series solution? It's something where I put in all perturbative data and all non-perturbative data. So the non-perturbative data is associated to these exponential factors of the instanton action. And you see that I'm summing over n and m. So there's plus n and minus m. So there's the two instanton actions. And then I have to add perturbative data around the perturbative vacuum, but also the perturbative expansion that I can do around any nm, so n/m instanton sector. So these guys here, these phi and m's, they basically look like what they're here. So you see, again, I have to compute a bunch of numbers, these ones in black, but now, of course, around the nm instanton sector, not just around the 0, 0 perturbative sector. But you can do this. They have different starting orders. There's some coefficients there. You also have to compute. And there's some logs. There's also some logs that appear in this when you try to do this. Now the logs are...
Ricardo, can I ask a question? How do you go about...
Please interrupt at any time. So I'm sorry.
Yeah, this is Gabriel. How do you go about in figuring out this ansatz with the logs?
So that's imposed by you again by resonance. So when you try to put an ansatz that doesn't have logs, you basically will not be able to solve Pauli-1. So you realize that the only way to make the recursions work, because you have to make highly complicated recursions, which now will involve all these non-perturbative sectors, you realize that you need these logs to make the thing work. And I will come back to later in 2 slides to another reason why the logs should be there, which is also associated to resonance. So ask me again if when I show you the plot, it's still not clear why the logs appear. But let me say something more about the logs, which is you should say, wait, hang on, didn't you just tell me that there's just double pole singularities? And what were you talking about? Yeah, I mean, the log sectors are not only independent, so they satisfy a recursion, which is, well, not a recursion, this is triviality, which is written here. And so you can reorganize. So this is just the simplest way to write the trans series. I mean, I will talk about trans series resummation in about half an hour. It's just the simplest way to write it. And when you do the resummations, the logs go away. And basically, I mean, there's really no log singularity. It's just a way to organize a trans series, and as I will show in a plot later, to split resonant sectors. Okay, so we compute all these numbers. We have actually computed a lot of them. I think thousands of them, to be honest, on the computer. And you can ask, okay, so that's and I'm sorry, I should have said something else. And the trans series, of course, depends on 2 parameters, sigma 1 and sigma 2. Because why? Because I have a order 2 differential equation, so boundary data is 2-dimensional, and I need 2 parameters. How do you know that these things are in fact resurgent? So we don't have a theorem. We have basically a lot of checks. And what we do is we use this large order resurgent formulae, and we check to very high accuracy that things are going well. So here, I mean, I'm looking at the growth of some perturbative sector, which goes as g factorial divided by exponential of g times 1 over g corrections from the 1 instanton, the 2 instanton. So here's a plot. The higher instanton sectors are predicting the growth of the perturbative sector. Remember that this problem here is resonant. There's instanton actions a and minus a, so the picture is slightly more complicated than this. It looks like that. There's the a and the minus a, they both contribute. And already at perturbative level, the leading asymptotics is distinct. There's a term here in a, you can see here, and there's a term here in minus a. And of course, this is associated to the fact that the perturbative series goes as gs squared, whereas instanton sectors go as gs, the perturbative series. Here's a check that Pauli-1 solution trans series should work. So what we're doing here, this is log 10. So we're comparing the prediction for the growth of the U, so the specific heat, from resurgence, so from a formula like this, compared against the exact things that you can do recursively in the computer. They're just rational numbers. So you're trying to see how good can I predict these rational numbers. And so here I go up to Geno's, let's see, 30, and I put 9 instantons, and the accuracy has, well, roughly above 70 decimal places. So I mean, this is very convincing, I think. And we have many of these checks to see that the solution should be fine. All right, so let's assume that I have the solution. Let me show you once again. I mean, you don't have to memorize this formula, but so I have this trans series, and now I want to extract numbers out of them because I want to study non-perturbative physics around GS. And I have these phi's here, and they're asymptotic series. So you'd say, well, but you just told me that you can't get the number out of those guys because they're asymptotic. The radius of convergence is 0. Yeah, okay, so what we have to do is the following. We have to do a resummation, which goes in 2 steps. So the first step is that I grab each asymptotic series, and I have to do Borel resummation. So that's just an integral that you have to do. You can't always do it. I'll come back to that in a second. But whenever you can do it, you just do it. And that gives you the trans series building blocks. And then you have this resum. There's an S there from summation. And then you can talk about, somebody has a question?
Yes.
Yes, go ahead.
So you say you have both positive and negative action.
That's right.
How can you have both together? I mean, then you have a small g and large g.
That's right. But that's so if you think about it, let me see. Okay, let's go back to. That's something that looks like this. So I mean, not necessarily in the phases of your system, you're always in a perturbative phase. And so from the point of view of Ponlevée is the fact that you have these 3 types of solutions. And when you're here in the general solution, you basically will not see any square root decay. So you will not see any perturbative part. Everything is highly non-perturbative. And in fact, the exponential suppressed and exponential enhanced guys will play the game at the same time. But where's the trans series? There. But not necessarily sigma 1 and sigma 2 are both non-zero all the time. Well, they have to be for that general solution. But when you start off with your perturbative solution, they can even be both 0 basically. And then only upon Stokes transitions, you will see the non-perturbative content come about. But I'll talk about that in a second.
Mm-hmm. Thank you.
Which is in fact the next slide, the next bullet point. The next bullet point tells me that once I have resummed these building blocks, I need to do, which I've called Borel resummation. I need to do what I call a Cal resummation. So that's Borel came up with the analysis of all these asymptotic series, and the Cal told us how to put all these things in trans series. And so if I want to do the resummation of the trans series, I am doing the resummation of all those guys there, but I still need to sum over all these trans series building blocks. Basically, I need to sum over n and m. And there's the sigma 1 and sigma 2 that Zé was just asking about. And so that's the third bullet point is, I think, the answer to what he was asking is that this only holds in Stokes wedges on the Borel plane. So sigma 1 and sigma 2 change as I cross the Stokes line on the Borel plane. So I need to have Stokes data if I want to grab this trans series and take it non-perturbatively across the complex plane. Otherwise, I'm just attached to a, let's say, quote unquote, perturbative wedge on the Borel plane. And as I said, the 2 parameter is also resonant. So I still need to understand how to deal with that n minus m. When n is equal to m, all diagonal non-perturbative sectors have the same weight as the perturbative guy. And I need to know, again, that can only occur in a situation where both sigma 1 and sigma 2 are non-zero, so a highly non-perturbative case, but I still need to know how to handle that diagonal properly. So in order to understand what to do with resonance, let's just talk a little bit about trans series when I have more than 1 parameter. So to try to understand, sorry, I was pointing on the screen, not with it. To try to understand how to deal with this n minus m guy, let's just imagine a situation where I have an arbitrary number of instanton actions. I mean, it could come from one of these minimal strings at the kth level. But let's not worry about that. Let's just be completely general now. So I have k distinct instanton actions, and I write a trans series that looks like that. So it has k parameters. Each perturbative, there's only one, and the other ones are all non-perturbative. Sectors is labeled by n, which is a vector in zk, and they're asymptotic series like that. And there's a over there in the exponential. So where are the Borel singularities of this trans series? They're obtained by a projection from the lattice, basically from this trans series lattice to the Borel plane, and that's done by just basically the inner product with instanton action, which is, if you want, is just the argument of the exponential. That's how you locate the Borel singularities. So there's where they are. What are they? Well, they're in this class, which is known as simple resurgent functions. I mean, again, this is not a theorem. This is something which is a bit empirical. So far, all examples we've studied, they're always of this class. This need not be the case all the time, but that's what we found so far. And what are simple resurgent functions? Those are the ones whose Borel singularities are poles and log branch cuts, nothing else. So they're relatively simple. And what do these singularities look like? So here I'm looking at the nth sector, and I'm looking at its lth singularity. And so I'm never going to write poles. They're always easy to add in, so I'm just putting the logs. So you have the log branch cut over there around the lth thingy. And what do I have in front? And that's the origin of this name of resurgence. I see the resurgence of another sector, the sector at n plus L. So if I look at the lth singularity of the nth sector, I see the resurgence of the nth plus L sector. Up to this number here. That's, we're calling it the residue because it also appears in the pool. Those are complex numbers, which are, well, they're basically associated to Stokes data, as I'll show in the next slide. They're basically, well, in 2 slides. If you know the Borel residues, you know Stokes data. If you know Stokes data, you know Borel residues, vice versa. So these are the hard numbers. They're transcendental numbers that still need to be computed, and we need to know what they are. So here's a plot of what's going on. So I have my trend series lattice, if you want. I mean, they're in ZK. Here I'm illustrating in 2 dimensions, and I'm projecting down to the Borel plane. So here I'm showing you these dots here. These are the non-trivial. There's a reason why it's not the full lattice, but just a couple. The non-trivial singularities of the 3, 2 instanton sector in a 2-dimensional case. And what I'm telling you is that if the kernel of the projection vanishes, basically that's the plot here on the left, the problem is non-resonant. That's not what we're dealing with. We're dealing with resonant problems where the kernel is non-vanishing. As you can see, different guys, they drop on top of each. So this is the Borel plane here, down here, in 1 dimension. So they drop down on top of the same singularity. And this comes back to the question of Gabriello, why the logs? The logs are telling you apart somehow. It's the way the trend series tells the fact that on a singularity, I have several guys on top of me. And string theoretic examples, well, let me say, the string theoretic examples we have studied, let me not be too definite on this, are always resonant. And again, this is a way to include both open and closed strings because I need to have expansions in GS and expansions in GS square, depending on which sector I am. And by the way, it's not only the 0, sector, which has a GS squared expansion, and any n/n sector will also have a GS squared expansion. And the way that's achieved is via resonance. So I need to understand how to deal with this. In particular, I need to understand how to, sort of, quote unquote, disentangle all these guys that lie on the same Borel dot.
Ricardo, can I have a question?
Sure.
Is this phenomenon of resonance related to the, for example, in SQL1 string theory, the D-brain actions, there are MN ZZ brains, maybe, and their actions for MN exchanged, they are the same. So is it the same thing?
Oh, we think it is, but we're not sure it is. Let me put it this way. So that's associated to doing the semi-classical decoding of the full 2-parameter trend series. We've done decoding of the trend series, which is to say, give a semi-classical description of each block in this lattice. And we've done that for basically the lower boundary. And we think that the higher boundary, the higher members in the lattice are described by the representation theory of minimal string theory. We're not completely sure because the instanton actions match, but we have not done the calculation yet for 1 and 2 loops around the instanton, which we have to do. So let me put that, the answer with, it looks plausible, but we don't have a definite answer yet.
Because this Z brain actions, they're precisely instanton actions.
Yes,
so
right.
That's right. Yeah. Just then I wanted to make a comment that well, I'm not sure it's well, it can be done. Well, one can write nice differential equations describing this theory. But if you introduce, for example, sine Liouville perturbation in this theory, which describes like a condensate of tachyons in SQL1 string theory, this removes the degeneracy. So maybe this would provide a stringy example without this resonance.
Maybe. So again, all the examples we've seen, and we've done minimal strings, we've done matrix models, we've done topological strings. They've always been resonant. But okay, I've not done all of them, of course, so I cannot make it.
Just an idea, maybe.
Yeah. It's a good idea. I mean, it's worth definitely checking.
Okay, thanks.
All right. So we have to deal with this resonance. And so, which is this plot here. Let's just backtrack. And we have to look at the singularities of the Borel, of the Borel transform of these end sectors, which are given by these Borel residues in order to compute Stokes data. So remember, that's what we're trying to do.
Ricardo, sorry, could you elaborate a bit more on these pictures? So you have this vertex at which you have this branching behavior. So are these the points that appear on the form on the previous slide?
So
you have,
okay, okay, let me move forward. So we have here a lattice of all possible building blocks of the trans series. And when I focus on the 3,2 sector, it turns out that the only people that can have singularities are, so that's sort of these people here in this lattice. So that's why I'm not showing a full Z2 lattice, I'm just showing a bit of the lattice. Those are the, let's say, possibly allowed singularities. And then down here, this blue line, that's the Borel plane. So I'm projecting, remember that I'm projecting from the lattice to the Borel plane to know where the singularities are located. So I'm projecting from the lattice to the Borel plane, represented by a line, to know where singularities are located. Is that what you're asking?
okay, thank you.
All right, so again, we're doing this projection to know about Borel residues. How do Borel residues give you Stokes data? That's the next question. So for that, we need to look at alien derivations. So that's basically an abstraction of this singularity. So basically what you're saying is that at the L singularity of the n sector, I find the n's plus L. There's a log branch cut, so I can look at the discontinuity of the log. This is, I'm cheating. It's not exactly that, but that's morally what's going on. And so delta sort of measures, again, I'm cheating, the discontinuity. It's actually measuring a nonlinear discontinuity, but let's, for the sake of argument, it's not really worth going into the exact definition. So the discontinuity of the nth sector at Lth guy gives me back the nth plus L. And now when I write it in this formalism of the discontinuity, I find the object there is slightly different. And that's the inner product between a k-dimensional vector and the location of the n guy, the nth plus L. And that's basically the vector of Stokes coefficients. So that's what I need to compute. This is the infinite set of transcendental numbers, which is hard, and which for polynomial one, only one number was known up to a little while ago. There's this constraint that not all lattices have a non-zero Stokes vector. There's a lot of zeros, and the lot of zeros again is done in this plot. So basically, I can move sort of one. So here I'm on the 3,2 sector, and this is a picture of what the alien derivative is doing. So I can jump forward or to the right if you want once. I can jump up only once, and then I can jump back. But if I try to jump to this point here, the Stokes vector will be zero. So there's no discontinuity. So those are these constraints here. That's what they mean. And if I know Stokes vectors, I can find the Borel residues and vice versa. Here's two formulas. So for instance, the Stokes vector at -2 jumps is the Borel that jumps twice, and the Borel that jumps once, and then once again. And there's formula like this. I mean, this is all very combinatorial. And that's the picture. So this is what I'm looking for. I'm looking for Stokes data for polynomial 1, and the Stokes data should organize into sort of a lattice of vectors, which is mostly on the third quadrant, a little bit on the second, a little bit on the fourth, but mostly on the third quadrant. So what are these guys? Okay, before that, why do we want these guys? Let's backtrack again to the motivation and see why do we want these guys. The reason why I want these guys is to cross the Stokes line. Remember, this is the Borel plane. Here are the singularities. The left is not equal to the right because I have to sum over all those Hankel contours. Now we know that the Hankel contours are associated to these discontinuities of the logs. So that's sort of I have a picture of how to put them. And in the simplest possible example, where I go along direction, well, let's say X. So I go along here. I just pick this guy along the X direction. It only has one component, the first component. So this vector here, it's going to be something, 0. And the jump, which is done, represented here, when only this Stokes vector is considered, is basically implemented by the Stokes automorphism. So the jump from left to right is implemented by the exponential of the alien derivative. That's the relevance of the alien derivative. And basically what it does is that the trans-series parameter sigma jump to sigma plus Stokes state. And again, this is when I'm just having this guy working. If I have these back guys, the transformation is much, much more complicated. I mean, it's nonlinear, but but that's the simplest case, and that's the idea. And so this is to say that there was some questions before, I think, that you can be in regions where the sigmas are 0 and you're sort of quote unquote perturbative, but once you start moving around, then the sigmas will jump by Stokes data. There will be phase transitions, and I'll go into non-perturbative phases of my system. So I need to tell you one more thing. This is slightly technical, so I mean, but it's relevant because this is the first conjecture we made in order to compute all Stokes data. I can abstract slightly. So remember, this was the alien derivative. I can abstract slightly this operation to have something which depends on arbitrary vector v. So I call it g instead of delta. And this satisfies closed commutation relations. But there's a vector there, v, there's a vector there, u, and there's another vector there. This is a slight generation of the alien algebra, because when you specify to the alien derivatives themselves, so the vector is now SL, that's what you get. This is obvious. But this is only, this is the algebraic structure of the alien lattice is only closing if this combination you have here is proportional to Stokes data at the nth plus L plus m sector. So this is a highly non-trivial requirement. I mean, it need not be true in general, and we found that it's, well, we found numerically, and so we conjecture that it's true for polynomial 1 and polynomial 2. And if you know this, then you can find the Stokes automorphism. Now, this is, sorry for this technical aside, but this is sort of the first step that allows us to go through. All right, so now let me show you the results. So the train series is resonant, an minus a. The kernel is a non-trivial projection because the kernel is a span of the 1-1 vector, and basically alien derivatives organize into sort of symmetric positive and negative directions. Okay. So here's what, let me just show you the pictures. Let's forget the formula. Here's what the lattice looks like. Everything is organized along directions of the kernel. And these guys are projecting down on the Borel plane. Again, not all of these need to have non-zero Stokes data. I'm just showing the arbitrary lattice. Everybody comes down here. And the way that we tell different sectors apart from the point of view of the train series is by looking at this log sector. All right. So do I have to compute an infinite amount of numbers? So that's sort of, you will start, when I suggested my students to do this, they probably were not very happy when I told them, let's compute infinite amount of numbers. But it turns out we don't have to compute an infinite amount of numbers. So the train series is resonant, again, as I said. There's a non-trivial projection. The diagonal sectors, they all have a closed string expansion, GS squared. This means that the Borel residues, they're sort of, I only need sort of quote unquote half of them. Again, let me show you a picture. If I know the people that are down the diagonal, I know the people that are up the diagonal. So this formula here, let's not worry about the formula, just tells me that if I want to compute this 3-4 comma guy, the red, it's equal via that formula to the dash red. The blue guy is equal to a sum of the dashed blues. The green guy is equal to a sum of green blues, and so on. So I only need to compute, instead of infinite numbers, I need to compute half of infinite numbers. That's still not very motivating, but morally speaking, you feel slightly better. Okay, what else can you do? It turns out that you only need diagonal Borel residues. So you only need the people that come from the diagonal. You don't need to be going into arbitrary sectors. So that's, again, you went through half infinity to less. I mean, it's one dimension less of infinity. Instead of two-dimensional infinity, you have one-dimensional infinity. If you know the guys on the low side, you know the guys on the upside, and so on. And if you know Borel residues, because they relate to Stokes data, they can be generated recursively. So the dots here are things that I compute, Stokes data I computed before, and I compute the next and the next and the next. So it seems like I don't have to compute a lot of guys. All right, so let's populate these guys. So we first need some guesses to occupy these guys. And the first guesses we had were back in 2011. Well, okay, let me take that back. It's not guesses, it's numerical calculations. So the first numerical calculations we had were back in 2011. We're using some method of asymptotics. And we tried some guesses with this, which turned out not to be correct, but well, we had very limited data. So that's what we had. And then last year, we implemented a different method that I have, very smart students that came up with a completely different method to do this calculation. And we managed to populate a lot of this lattice. And you would say, well, can you do more? Well, this is a slow procedure. So here I'm just going, these are different S1, S2, S3 are different diagonals. 1, 2, 3. And X, I'm just going down the diagonal. It's basically the X, it's basically the X position here on this lattice. And you can see that the precision drops. This is how many digits you get. The further you go out on the diagonal, the more, I mean, here you already only have 10 digits. And the timing also is really, this is the machine, my students were using. So you quickly get to 7 days. So I mean, in order to do this thing, you really are a couple of weeks of dedicated machines just computing these guys. So we had numerics for this, and now we want to go analytic. So how can we go analytic to find these guys? Well, the first thing is this, what I just told you before, which is if you want the algebraic structure of the alien lattice to close, you need a requirement to hold. And we found, well, for the guys we tested, that it holds numerically, that in fact this is true. So we conjectured that this would be true for any member in the lattice, and that gives this structure of Stokes vectors. So you see that there's a sort of integer numbers there, and then there's a proportionality factor, and that's all we need to know. And these are reconstructed from the diagonal guy n just to s, 0 guys alone. So again, I mean, we're getting less and less and less numbers that we need to compute. All right, so that's what the lattice is now looking like. So, you know, you see the integers vectors plus the coefficients. And then the next question is, okay, what are these coefficients? And then, you know, after my students stared at them for a couple of months, I would say, they come up with this amazing formula. So here we're walking down the first diagonal. So here you see the 1, 1, 1, minus 1, minus 2, minus 3 is coming down the first diagonal. And let me just show you, this is going down the second and the third diagonal. So you say, okay, let's go slower. So you see that there's 1, 1, 1 there. That's the first, 2, 2, 2, the second diagonal, the third diagonal. And you see that there are numbers here, 3 from the third diagonal, the 2 from the second, 1. Then there's zeta numbers. There's a lot of them. And then there's even weirder combinations that you get 1, 2, 3 here in the zetas. And all that you need, so I mean, and we have all these guys. And all that you need is the 0 and the 1 at each diagonal, the 0 and the 1 at each diagonal, the 0 and the 1. So the purple people is the people that we still need to put in. Turns out that, again, you need even less than that. Of course, I mean, now you're needing less and less because we're already telling you a lot of these numbers. I mean, we're telling you about these zeta numbers. We're telling you about these combinations of zeta numbers. So we're already telling you a lot about the structure to tell you that you need less and less. And so it turns out that also you don't need, as you go up in diagonal, it turns out that everybody is related to the first diagonal. So once you know the structure, and that's a really hard work, then you can tell that everything goes down to knowing 2 numbers. The first one was the original Stokes number that was known to people for many years, was computed first by François David in 92, I think. And the second one is this one. So again, we had to struggle a lot because of that guy there. It was unexpected, but that's it. So, so we have a conjecture to tell you what all Stokes data is for this guy. For polynomial 1, for polynomial 2, we believe that this also builds up on some closed form asymptotics to sort of set up a system to compute some of these guys. We have generating functions for everybody. And we believe that this probably works for any polynomial. Probably any guy in the KDV or KP hierarchy should work. This is what they look like, and here are the numbers. Okay, so just to show you, I mean, again, these are numbers that are computed with analytic expressions. Okay, these are not just numerics. So we have everybody, and as you go down each diagonal, these things behave rather nicely. They're just humps and humps as you go down. All right. So
sorry, Ricardo.
Yes.
Yeah, I didn't quite understand the status of the conjecture. So once you understand these structural properties, can you actually compute analytically the second number N01, or you still have to match to 7 digits?
This one, so this one here, is the only thing that at the end of the day you have to guess.
So, okay. And there's no physical understanding whatsoever.
We think that there might be. That was what I was trying to say to Sergey before. So this may come from a CFT calculation, but we're in the process of trying to see what CFT calculation will provide for that number. So in this paper, we're basically telling you this is all the numbers. And now we're trying to see how can I explain physically. That was the question I had at the beginning. How can I explain physically Stokes data? That's what we're trying to do now. Okay. But I have nothing to say about that for this talk. Sorry. Maybe next year.
Thanks.
Where was I? So, okay, we have all these numbers. They give all these bumps, and that's it. And we have generating functions for everyone. So you could say, okay, now we have analytic expressions for all Stokes data. We have the trend series. We should be done. So now we should start being able to analyze non-perturbative results going out in these phases. So remember, these were the pictures we had seen before. how can I access the tri-trunqué phase, the trunqué phase, the general phase of Pont-Levé-1? I'm just going to talk about tri-trunqué, okay? It's simple also. I think 20 minutes, right? Is how much I left. That should be okay. So I'm going to show you lots of pictures now. All right, so how do we go? So we have Pont-Levé, generically has double poles. They are simple zeros of the partition function. So remember that you can think of this as Lin-Yang zeros. So these describe different phases of our system. And let's just focus, we're just doing the tri-trunqué. Sum over all the instantons, and then I sum over G. Is that meaningful at all? There was, well, I cannot highlight, I can highlight. I hope you're seeing the highlight. There was a factors beta, there's starting order. So this game is only reasonable if the starting order is, let's say, wants to play the game. It turns out that it does because they're linear. Let's see this in the plot. So now I'm not showing you, don't be confused. I'm not showing you the lattice, the two-parameter train series. I'm showing something else. It's also a square, but it's something else. So here is instanton number n, and here is the G of the sum over genus. And what I'm saying that it's, so the green guys are the non-zero coefficients at each instanton. And what I'm saying that beta, the starting order is linear, means that basically that's how it goes. And so you could ask, can I sum over this red arrow? And then the G string sum would be the next red arrows. And this sometimes goes by the name of analytic train series summation in the mathematics literature, where it first appeared, by the way. It goes by the name of transymptotics, the two Castin. And this is possible. So what you do is that you introduce a sort of a new variable, which includes the exponential in Z and also square root. And then the resummation, it becomes a sum over just G's. So these are the red arrows. And each red arrow, it's a guy that looks like that. And you'd say, well, but all these things were asymptotic. Now you're not doing any Borel summation. Is this something which is well defined? Surprisingly, yes. So these guys, these U functions, the red arrows are convergent series. Asymptoticness is all kept in the final sum over G string, if you want, Z. That's quite interesting. So for Pont-Levé-1, I'm just going to show you the first guy. Actually, by the way, if you just use a more adequate variable, U0 satisfies the Weierstrass. So as it has to be, because in some sense, quote unquote, Pont-Levé-1 is a nonlinear generalization of Weierstrass. And at leading order, you get an exact result. Looks like that. That's a very convergent sum, which is what you expect because it has a double pole at tau equals 1. You say, but tau equals 1 is a point? No, tau equals 1. I still need to invert this guy to go to Z. And that's sort of the inversion. It's analog to the Lambert W function. So that gives you an array of solutions. And the array of solutions that you get is basically these guys here, dot, dot, dot. You get all those guys there. And then, where was that? And then you can go to subleading results, and they will iteratively yield the following arrays. So if you do the next guy in GS, you get that line over there. Can I find them all? There. And then if you do the next guy, you get there, and so on. And so you get them array by array by array by array. You say, okay, that looks interesting. Can I do better? What happens for the partition function, for example? The partition function, again, I'm showing you the n, the instanton number, and here G, the starting orders. So it's only non-zero on the green dots, on the green box. And this linear transymptotics that we're doing was just that arrow, actually. It's 1 minus tau. It's quite simple. And then you can say, okay, I can go on and they go on and go on and go on. Yeah, okay, I get the same. Or I can try to do something which these green boxes are yielding at me, which is, hey, I'm growing quadratically. I'm not growing linearly. So what happens if I do this quadratic resummation? And it turns out that if you do the quadratic resummation, you get the lattice. Okay, they're not all at the right positions because I still have GS corrections. But globally, the picture is there, and all I have to do is small GS corrections to put the lattice properly there. So I mean, I can really access, oh, I have another picture. I can really access non-perturbative information really easily by just doing this quadratic transymptotics for the partition function. What does it look like? Let me be slightly schematic here. The train series summation for the partition function is going to look something like that, where each of these Z, Z1, Z2 are some adequate functions. So let's look at Z0 with some parameters, tau hat, I just put some numbers there. Q hat, by the way, this number, I cannot highlight it. Okay, let's not worry. This number here, 2 to the 5th, 3 to the 3/2, is part of one of these, of the second number that we had to compute to get all the Stokes data. And then the first guy, Z0 there, this is the result. This is quite interesting because if you only had tau and q, this would be a Jacobi theta function, deformed by the Barnes. And then, okay, let me be quite schematic here. Then if you want to go to parameters, there's going to be extra factors, some polynomials, there's going to be some polygammas and so on. So I just, for the moment, let me just, time is running short, so let's not go into these technicalities. The way to properly, again, the same, akin to what happened with Stokes data, the way to properly write this partition function is going to be by modding out by the kernel of the projection and by using resonance. And this is ongoing. So let's not talk about that. Let me just make the best of the time, 15 minutes. Let's just talk about matrix models, a few pictures about matrix models, and then JT gravity. All right, so can we play the same game for matrix models? Now, I'm not going to tell you again all the technical details. I'm just going to show you pictures, basically. So here's the one matrix model with polynomial potential V. And I think everybody here knows very well that in the n-to-infinity limit with T as the Tuft coupling fixed, the free energy has a genus expansion. You can also have Dicraft-Calabi-Yau duals. Let's not talk about those. Here's a simple model, the Gaussian matrix model. Probably everybody's seen this. And this is very easy to do. The canonical partition function is a triviality to find. And if you compute the grand canonical partition function, this is what it looks like. And that's why I just showed you that previous formula. The leading, where was it? Here, remember? That's the same formula. So you see that is the formed theta functions, the formed quote unquote, by the Barnes, are appearing everywhere. And because they're very naturally associated with the grand canonical version of the Gaussian, this is indicating that there's some leading order universality for all double scaled models. So somehow the non-triviality is going to be in the higher people. But okay, but the Gaussian is exactly solvable. That's not what we want to do. Let's look at the quartic. There's the quartic potential. Generically, it's three-cut solution. We're actually going to be dealing with the symmetric potential. So this plot is not symmetric, but anyway. And we've worked out quite a few years ago already, the one-cut and the two-cut trans series. So here I'm plotting the holomorphic effective potential. You see the one-cut solution and the two-cut solutions. We computed instantons. We computed a trans series for these guys. Again, I showed you the string equation on one of the first slides. This is the analog of the Ponlevey one equation. This is the discrete Ponlevey. R double scales to U. This is what it looks like. And it turns out that the trans series is very similar. So let's not go into all those details that I described for you for Ponlevey back half an hour ago, but it's very similar. Only that now A depends on T. So let's look at some pictures. If A depends on T, I can actually, so this is a Tuft complex plane. And if A depends on T, I can define anti-Stokes lines. These are phase boundaries for this system. And what we have. So here's the picture. So in blue, with the one, we have the one-cut phase. That's where eigenvalues cluster into a single cut. And in lighter blue, with the two, we have the two-cut phase, where eigenvalues cluster into two cuts. There's that dot P1 and that dot P2. Those are the double scaling limits to Ponlevey 1 and Ponlevey 2. Then there's a green region, which, in this resurgent business probably should be called an anti-Stokes phase instead of a Stokes phase, like the blue ones, where eigenvalues cluster into three-cut configurations. And then there's generic pink, red, whatever, color, where they cluster into tree-like structures. And this is the analog of the tronqué, the très tronqué in blue, the tronqué in green, and the general solutions of Boutreau for Ponlevey here for this case. All right, so let's move along this direction here on the Tuft plane. And let's see if we can play the same game with these zeros/poles. And by the way, remember that now we have all Stokes data. I've computed that a long time ago. Well, half an hour ago. And it turns out that if you know Stokes data for Ponlevey, you can undouble scale it to the quartic matrix model. So, I mean, there's some formula, and so you basically know everything. And so let's start with some numerics. I'm plotting here the recursion coefficients Rn. So remember that matrix models can be solved by orthogonal polynomials. And the way that I generate the different orthogonal polynomials is by a recursion, which involves some coefficients that satisfy the finite difference string equation. Those are those Rns. And I'm plotting them here. You can recursively do them numerically. This is the log of the absolute value. You see that here in the blue region, which is the one cut, they're very regular. And in the green region, which is the anti-Stokes, they oscillate. And here I'm showing you the phases. And you could say, does your train series, you could ask, does your train series reproduce all these? I mean, clearly there's a transition that's going on, and it's, as I will show you in this slide, it's highly non-perturbative, because the perturbative part of the train series alone can reproduce the behavior of these R guys there very nicely. But as soon as you move into the three cut, that's it. It doesn't know where they are. So you can ask, what happens if I add one instanton? Yeah, okay. The one instanton can tell you there's some non-perturbative physics going on once I do this, once I cross this phase. And you say, yeah, well, but it only sees, it doesn't see that there's these oscillations here. It doesn't even see the first bump. Let's put in one instanton. Put 3 instantons, yeah, it's still not that great. So what can I do? Well, let's try to play the game we played before for Pont-Levé, where we did these linear transasymptotics, where we found the first array for the Tronqué solution, the first array of poles. And if you do that, oh, I see the first bump, there it is. But I don't see the next bumps. This is leading order in GS. How can I see the next bumps? Well, let's do next to leading order. I see the second array, right? Like I had for Pont-Levé, I see the second array. Now I see the second bump. And you say, well, I would like to have the full structure. Of course, you have to do quadratic transymptotics. Again, you see that dot is not right on, that dot is not right on. So there's still, this is just leading order in GS. So there's still higher order in GS that I have to put in to put all these people in. And I can also reproduce the plot I showed you earlier on, which is the zeros of the partition function. And here I have, this is the numerical calculation. This is the one that comes from transymptotics resummation. All right, so, well, 6 minutes. Let me tell you about JT gravity real quick. So, all right, can we play the same game for JT gravity? So let's reconsider JT gravity in IDS2. And let's quickly just, I just have to remind you a couple of things about JT gravity, just that show you the matrix model calculation, but I have to tell you why is there a matrix model here? So the natural observables, the calculations that people usually do is computing macroscopic loop operators that create asymptotic boundaries. So remember that this is ADS2, R is equal to -2, and I have asymptotic boundaries with regularized length beta. And these macroscopic loop operators are usually exponentials of something. I'll tell you what H is in a second. So for the moment, just remember that. I mean, this is the same story as in the minimal strings. Macroscopic loop operators are computed by exponential type vertex operators. And if you compute the disk partition function, it turns out that it's one loop exact. That's the result. So remember that this guy, you know, by the Gauss-Bonnet theorem, is just a number. So S naught is the natural coupling, and then here is the non-trivial part. Turns out that this cannot be the full story. So you can, if you have the partition function, you can do a Laplace transform and get the density of states. And it turns out that the density of states you get tells you that you have a continuous spectrum. So this is not appropriately holographic theory. And you know, last year, Sachin and Sanford told us that holography requires actually that we sum over all higher topologies. So it's not only that we have to look at the disk, but we have to look to sum over all genus and all boundaries. It turns out that if you do this, you can get this duality that I will explain in a second in the next slide. So you're going to have two different pictures of the same correlation functions. Sort of the space-time picture where the coupling GS, if you want, is x to the minus S naught. I'm summing over all topologies, so all spacetimes with genus G and N asymptotic boundaries with those regularized lengths, beta 1 through beta N. And the way that I compute this is recursively, because these guys, as I'll show you in a second, are dictated by Weil-Peterson volumes. And so Misakani came up with a recursion a few years ago on how to compute all these Weil-Peterson volumes, and so I can compute all these guys. Turns out that there's a holographic matrix model calculation where, and now you see what the H is. I'm just basically, remember that the interpretation that we have here is that I'm doing a sum over a random ensemble of Hamiltonians, H, with some weights. I'll tell you what the potential is in a second. And I'm inserting these macroscopic loop operators, or if you want, these thermal partition functions. And I am sort of supposedly getting the same number. In the matrix model, the way that I recursively generate data for these guys is with the Renato-Rantin topological recursion. So why are these guys the same? Let me tell you first what each one of them is, and then you'll see why they're the same. So the first thing is what happens in spacetime. In spacetime, I have to compute these ZGNs. These ZGNs actually factorize. They have a piece, that's that piece there, which is given by the Weil-Peterson volume. So what are these guys? I look at the moduli space of hyperbolic Riemann surfaces. Hyperbolic, remember, R is equal to -2. So these are negative curvature surfaces. So they have a metric on them. with genus G, and I can use this metric to describe n geodesic boundaries of this fixed length B. And so the volume of these moduli spaces are the Val-Petersson volume. Of course, these geodesic boundaries are not exactly the asymptotic boundaries of ADS. So I still need to do this, the trumpet, right? So there's the contribution from the partition function that basically translates from the B's to the betas. And I need to integrate over all possible B's. Well, there's a factor in the measure because I can twist upon gluing. The trumpet can also be computed exact. That's a localization integral. And of course, the non-trivial analysis is going to be, and by non-trivial, I'm talking about asymptoticness. The G growth is in the Val-Petersson volume. So what I need to see is what are the growth of these guys. What happens on the matrix model? Well, what happens on the matrix model side is that, as I've just said, the Val-Petersson volume satisfy a recursion by Mirzakhani. And this was shown a few years ago, I'm not sure which year, by Enad Larentin, that this recursion is equivalent to the topological recursion with a very specific spectral curve. And that's what basically proves the holographic duality for you. And all you need for the topological recursion is the boundary data, which is basically the genus 0, one boundary guy, which is the disk. So you can compute everything. And this is the spectral curve that generates everybody, which can be associated, although, I mean, from the point of view of the topological recursion, all you need is the spectral function. You really don't need to associate the matrix model, but for us, it's interesting to do so, can be associated to Kontsevich type matrix model, where well, sort of slightly degenerate, as I'll show you in a second. So the perturbative expansion is asymptotic. This was already known to people before. So the question we have is it resurgent? And I have 2 minutes to motivate that it might be. So here's the holomorphic effective potential for this spectral curve. That's the holomorphic effective potential, looks like that. So basically I have eigenvalues, oops, sorry. I have eigenvalues all here to the left, and then I have non-trivial saddles on all these. There's an infinite number of non-trivial saddles that I have there. And you can compute the instanton actions for these guys. They look like that. And you can even compute the one loop around the Elf instanton. I'm sorry, around the Elf one instanton. You have to be careful here because you have sort of infinite number of flavors, quote unquote, of instantons. And then you can put as many eigenvalues as you want on each of them. And that's that contribution. So this can be computed directly from the matrix model. And then you say, well, what about constructing the trans series? To show all these resurgence. Well, the trans series, I have 1, 2, 3, there's L possibilities, infinite possibilities of non-trivial saddles. So do I have to construct a trans series with an infinite number of parameters? Well, maybe not. So there's a sort of an alternative, which is to look at, go back to the Kontsevich matrix model, look at the free energy of 2D topological gravity. It depends on an infinite number of KdV times, these TKs. And the description of this particular spectral curve, that's why I said Kontsevich type. It's not the full-fledged, I mean, lambda is not, everybody's not turned on. This spectral curve is sort of quote unquote degenerate Kontsevich matrix model, where I sort of truncate. I only have 2 free KdV times and everybody else is fixed. And it turns out that this curly F here, this specific heat in the T0 time satisfies the KdV equation. And furthermore, higher derivatives generate Val-Petersson volumes when T0 is equal to T1. I'm cheating here slightly because I only have 30 seconds to go. So I'm just looking at the constant part in the polynomial of the Val-Petersson volume. But okay, yeah. Indulge with me for a second. So I can generate these guys if I know this F. And now for this guy, I should have a standard trans series. I mean, this is in the flavor of the matrix model where the instant action depends on these T's. And it turns out, again, I think my time is up, so let me wrap it up. It turns out that this leads to resurgent relations for the Val-Petersson volumes. You can write equations that look like this. They're related to some formulae that Mirzakhani and Zograf found also a couple of years ago. So you can see that they already had some hints of resurgence in some of the formulae they wrote without ever talking about resurgence. And what we can compute is that it matches the Kontsevich matrix model instant action, so it seems to be consistent. And furthermore, it gives us the first Stokes coefficient for this trans series. So I mean, here we're still very far from computing the whole Stokes data for GT gravity, but at least we got one of these guys. All right, so I'm sorry, I think I'm over time, so let me just wrap it up. I hope I've convinced you that resurgent trans series work as solutions for Polynomial equations, for discrete Polynomial equations, for a lot of things. We've managed to compute the complete description of non-linear Stokes data. That's a lot of numbers. And once you get these numbers, you can start doing trans series summations, and you can compute movable singularities, movable zeros of the partition function, singularities of the specific heat, And that's a non-perturbative calculation. We're starting to get this extendable to matrix models or discrete nonlinear, whatever you want to call it. And ongoing, it seems to be extendable also to JT gravity. Of course, this is just opening the door to a lot of things that we don't know. These deformed, quote unquote, Barnes theta functions, they seem to have some modular properties, Stokes modular properties. We don't know what they are. We'd like to know. It seems to be possible to find closed form expressions for the full non-perturbative partition function. We're trying to do this, and it should be something which should be, there should be some sort of a general formula that should work in the double scaling limit, in the matrix model, topological string. It should match some considerations of Enard and Marinho from 2008. So we're trying to see, but then there's resonance, which is on top. So we're trying to see this. We still don't have an answer. And hopefully there's also a complete, maybe similar description of the resurgence of JT gravity, but well, that's still far in the future. Thank you very much.
Thanks, Ricardo. Are there any questions?
Yeah, maybe I can ask a question. Well, first of all, it's a very impressive talk, but going to the panel level 1 case, so you showed some exact result for this linear trans-series with summation, where you keep the first order in G string, but you sum over all instanton effects, right? Yeah. Can you get also exact results at higher order in G string?
Yes. Yes. I didn't show you, but yeah, we can compute. They're more complicated. They're more complicated rational functions, but yes, we can. And by the way, and let me be honest. The first time that computation was done was by Ovidio Costa. So we're improving on his calculation by going to the partition function. But already to Ovidio, this was known that you could go. I think he did up to the second, and we've done much higher order.
And at leading order, it was given by a solution of Weierstrass equation. So there was some modular property. Are they transferred to higher orders as well?
That's a good question. We thought a little bit about it. We didn't come up with anything, so we sort of dropped. If there was some sort of deformations of Weierstrass that would start giving you the higher orders, we never found anything that looked reasonable. But I mean, it could be our incapability to find. So maybe, but I don't know. We sort of dropped that line.
I didn't quite understand the difference between the linear trans-series and quadratic trans-series. Okay. You were looking at different observables?
No. Well, yes, I'm sorry, yes. Yes. So the difference is the following, is that the linear is done by looking at the specific heat, and the quadratic is done by looking at the partition function. And the difference is that, remember, there was this beta coefficient, there's a starting order for the genus, and for the specific heat is linear. And so, it's sort of, quote unquote, more limited. And for the partition function, it grows quadratically. And you can try to translate this back then to the specific heat, and it's going to be a really messed up summation. And that's why it sees so much more than the linear of the specific heat.
I see. Thank you.
Okay, thanks.
Any other questions?
Sorry. So what was the operator H that appears in the expression for the partition function of JT gravity? You said, so you have a trace of exponent of minus beta H?
Yes, so H is a random Hamiltonian. So that's, I'm sorry, I cannot see. Let me, if you give me a second, I will find how to, am I going back? Here. So can you see here? So
yes.
I'm basically what I have here is a matrix integral where the potential is the potential associated to the spectrum.
So there you have missing trace on the.
I do. Yes, you're right. I'm sorry. That's a typo. Yeah, sorry. There's a missing trace there. Yeah. Sorry.
Okay.
I'm sorry.
I see. So it's like Largian limit of this emission matrix model becomes a random Hamiltonian model. Okay.
Yes.
Thank you.
And because of the Enard-Dorantine theorem on the Mirzakhani relation, this establishes the duality to JT gravity.
Also, could you please remind me what were these functions G that deform the Jacobi theta functions?
Barnes functions.
Barnes functions.
Yes, it's a gamma function of a gamma function, quote unquote.
Okay.
One other question.
Yes.
So about the last part of your talk, so you mentioned that JT gravity was described by a degeneration of the Kontsevich matrix model. So,
yes.
What would be? I mean, could you translate the general Kontsevich matrix model in terms of JT gravity deforming the JT gravity side?
Maybe I don't know. I don't know.
What kind of degeneration? So the consensus
degeneration
model has more parameters, and you have to fix some of them.
Yes. Yes. There's more KDV times. So in the general matrix, in the general conservative matrix model, we have an infinite number of KDV times, and we're looking at the degeneration where degeneration. I'm not sure if that's the correct word, but truncation. Where let me see. Let me try to go back. Let me show you the slide. Give me just a second. Where is it? Here. So you see that you have all these TKs, so you have an infinite number of KDV times, and basically we are only allowing in the free energy T0 and T1 to be quote unquote fluctuating. Everybody else is being fixed. I don't know what would happen if these guys are also fluctuating for the side of JT gravity. I don't know if somebody in the audience knows, and I don't know.
I don't know either.
Any other questions? Okay, if not, let's thank Ricardo again, and well, also Miguel Tietz for the first talk, and we'll resume again in the afternoon at 2 p.m. Lisbon time. Thanks.
Thank you.
Obrigado.